Okay, guys, so I'm going to talk about raster and vector data model first, structures. Then I'm going to talk about map projection and georeferencing. They are the same thing. Then I'm going to end with geocoding or reverse geocoding. Is that okay? All right. So the raster and then vector data structures, the reason we have it is because we want to represent the real world. Okay, and representation of a real thing is called a model. Is that okay? The representation of a real thing is called a model. Okay, so the raster model, the vector model, they are trying to represent something that exists in the real world. Okay, so we are looking at something like buildings, roads, you name it, water bodies, yeah, estuaries, rivers. I mean, like you can mention it, can go on and on and on. Trees, vegetation, farms, farmlands, everything that is around us. Okay, remember that GIS is about geographical information. So the geographical objects, we find a way to actually model them. Is that okay? So to do that, we use the raster or vector data model or data structure. Are you okay? So normally the word structure and then the model can be used interchangeably depending on where you're actually looking at. The structure is how it's actually being kept in the computer. Are you okay? The model is the concept, the idea, but virtually they are all talking about the same thing. Is that okay? So the raster data structure, how does it work? The raster data in the raster data structure, we have space that is subdivided into a regular grid of grid squares. Okay, regular grids of square grid cells. So this is like tautology, but it's not. Regular grid of square grid cells. Okay, so if you have space and you decide that, okay, I'm going to divide up the space into, so if I have this space and I decide that, okay, I want to represent things in here. But then before I do that, I have an idea how to do that. I'm going to subdivide the area, okay, into regular, grids or square grid cells. It means I'm doing something like this, okay, doing something like that. So I'm creating squares, okay. So the squares are actually like in a certain or arranged in vertical and horizontal, or the rows and columns. That's what I really want to talk about. Okay, so this is how the raster data structure or raster data model. Of course, these are not squares. If you look at them, some are not square, but it's because I'm just trying to show you on the board. Okay, so now this is not the only way we can represent our world with a regular grid of square grid cells. We can also have different shapes that represent our world. Okay, now what we do or what is done is that you actually keep the value in every cell, okay, that relates to the kind of object that can be found there. Okay, also you can locate objects by using the row and column numbers. Okay, so what does it mean? It means that we can have 1, 2, 3, 4. Are you getting that? 1, 2, 3, 4. So this is row 1, column 1. So to identify this cell, okay, we need to just refer to the row and column numbers. So the location of each cell is defined by the row and column numbers. Okay, that is the whole idea of the raster data structure. Okay, now there's something called spatial resolution. I think last week I talked about it, that satellites imagery or photographs always have this thing to do with how fine the image looks like. Okay, when a photographer takes a picture of you, the reason it looks nice sometimes is because of the resolution. Not sometimes, but most of the time, it is something you can do image enhancement that will make it look more like nicer. But basically, if the camera has a high resolution, then you have a high resolution imagery. So the resolution is a property of the camera or the sensor. Are you okay? All right. So the raster data structure, after it's divided the area, the space into the regular grids of square grid cells, now finds a way to represent, and the accuracy of representation depends on the size of the square. Okay, so in this case, this square here actually has a certain area or a size, a dimension. So the smaller the dimension, the more cells that can be fit the same area. So you agree with me that if I subdivide all these cells into two, I'll have twice as many cells as I have at the moment. Is that okay? And then in that case, it means I can have, a variation, spatial variation. Okay, I can have, an interesting way of representing things on the ground as opposed to having larger squares. Okay, so it's very important for us to understand the raster data structure. Okay, now another thing we do is that we record the position of a geographic feature to the nearest pixel. So this is what we're talking about. In the computer, when we store an imagery, so raster is synonymous with images. We have the image composition is composed of pixels. So we have rows and columns of pixels that make up the image. So everything you are looking on your computer right now is actually made up of, rows of pixels and then columns. So that's why you can actually change the resolution of your laptop or your computer, your desktop computer. Everything you are seeing on a computer is raster. It uses the concept of raster. Why? Because television sets, yeah, they were there before computers, but then you realize that computers look more like what? Television sets, just like they do computation. Excuse me, please. All right, so in TV sets, you realize that you need a raster on the TV set before you can have an image. So as a TV set that doesn't work, doesn't have raster. So this is something I want to say, by the way. It's not supposed to be like part of what I'm teaching you, but obviously we have raster being the basic composition of an image or concept of storing an image. Okay, so here you can see we have what we call a lookup table that explains the values or map the values in the imagery to what they represent. Okay, so now there's a forest at 1. When you see 1, it's a forest. When you see 2, it means a cultivated field. And then 3 is the water body. So we can actually put in the values or associate values with the, the imagery. So that is the raster data structure for you. The value stored for each cell indicates the type of object. I've already said it. So we decide to store certain values in the squares that represent what the object is. Are you okay? All right. Color values can be used most of the time. When you take a normal satellite imagery from a satellite in the skies, you realize that you see the rooftops and you see the road tarmacs, being a bit of a dirty, brown kind of color or something like that. You get dirty ash color. And your rooftops, depending on the color of the roof, also shows up. It tells you what the object is, isn't it? It does. All right. And so the raster data structure, is very, very interesting and relates very much to an imagery. We need to understand how images are formed. Okay, now you can actually store values as integers or alphabets or combination alphanumeric, but most of the time we want to use integers to represent the values of the objects. So different attributes at the same cell location can be stored as different layers. So the concept of layers doesn't only apply to the vector data structure or data model, but also applies to what? The raster data structure. Are you okay? All right. So like I said, you can decide that instead of using squares, you can use, say, triangles, which are not regular, so they are different. You shouldn't be, fixated and stereotype about these models. People can come out with different ideas. So you have to take note of that. For example, the triangular irregular network is an interesting one. When you look at this representation, you'll be, if you be honest with me, I don't know if you agree with me or not, but I see this to be a surface. This is like you can work on it. When you actually look at it, you get the impression that we have or a rendition of a surface. Okay, so the triangular irregular network is a typical, variant. Okay, it's a typical variant to the raster data model. Okay, so we talk about several variants. So we have the irregular tessellation. We also have the hierarchical tessellation. So these ones, I'm not going to bother you too much about it. Exactly. But I want you to know that it's there. Take notes. It's not everything we learn in class that comes in exam. You have to take note of that. Let's look at the vector data model. The vector data model is made up of points, lines, and polygons. End of story. Very, very easy concepts. So points, we can talk about something like, tree locations, pole locations. We can talk about what else can be represented as points. Wells. Are you okay? So for these objects, they do not kind of, spread out. Are you okay? They are really, really compact, and then, they're not narrow or wide. Are you okay? So they are very, very limited in space, whatever it is. So we look at a pole. If someone is standing at a pole, when someone is looking out for you and standing at a particular pole, count the third pole, I'm there. It's a particular location. A well is a particular location. Meet me at a well. Okay, but when someone says, meet me at the lake, you begin to ask yourself, which part of it? Is it inside the water, outside on the bank, or where? Okay, we have 10 minutes. When it ends, please, let's use the same link to rejoin. Is that okay? So the raster data model is a bit different from the vector data model, in the sense that the vector data model is more like making a sketch. So you're making use of a point to represent the pole. Okay. Meanwhile, you talk about what the raster will do. The raster will have to divide the whole area where that pole is into squares. All right. So we have the vector also making use of lines. So lines, what objects in the real world can be represented as lines? We're talking about railways, rivers, talking about footpaths. Are you okay? Can talk about insects, transects or something like where insects walk, and there are lots of things that can be represented by lines. Are you okay? Polygons, a farm is an example of representation of a polygon. We can also talk about football field. A football field can be represented by a polygon. A lake can be, we can use a polygon to represent a lake. Is that okay? Etc. So that is the idea of the vector data model. Are you okay? The vector data model, we have points, lines, and then polygons. Is that okay? So let me share this screen with you. So obviously, in this case, that's some kind of river. That's a lake. That's a pole. Okay. That's a building. It looks like a building, doesn't it? Okay. So we can have these three representations: points, lines, then we have polygons. Okay. So this is called the vector data structure or data model. Okay. And then we can have, like I said earlier on, we can have the raster data model. Okay. All right. So that is what I want you to nodes for now. They have their own advantages and disadvantages. Is that okay? So here we are also, I'm also trying to show you, you know, again, I'm emphasizing again on points, lines, polygons. So apparently lines are made up of points, polygons are made up of lines, which are enclosing. Is that okay? Obviously, when we look at the topology concepts, remember we had arc node topology. So yeah, this is how points are stored. They are stored in the tabular format. Point one has its own attributes, and the basic attribute is the coordinates. Every point should be defined by a set of coordinates. We can also store attributes at that point, such as how deep the point that place is, how high that place is, the name of the place. We can talk about you know, different things that happen at one particular place. All right, all that will be stored in the direction to the right. Okay, we can, as we move to the right, we'll have that. Okay, so lines here, we are trying to store lines in the computer. And so we have lines are made up of nodes, beginning and the end node, first and last node. We can add some attributes to that, the line. Okay, we have polygons made up of lines. Okay, so the polygon is made up of arcs. Okay, so polygon A, we can associate some attributes with it, and then we can have some nodes that define that polygon. Is that okay? So yeah, please don't worry yourself about the different implementations, the spaghetti model, the hierarchical vector model. Please, I'm not interested in that for now. So you can skip this one. Is that okay? All right. Okay, so topology is, you know, consistent or analogous to the vector model, because we talk about connectivity, which is lines. Okay, arc nodes are points. Okay, so that is basically it. Now here I'm talking more about the raster and vector. So the right and the left image, one of them is raster, the other is vector. So let me ask you, Richard, what do you think, Thomas or Richard, which one of them, P or Q, P and Q, which one of them is vector, which one of them is raster? Or mute yourself and answer for me. P diagram Q, which one of them is raster, which one of them is vector? Richard or Ima, or yeah, anybody can try for me. Which one of these is raster? Which one is vector? They are not even listening to what I'm saying. Okay, let me go on.
Sir,
Yes.
Q is vector and the P is raster.
Okay, you are wrong. Okay, you are not listening. That also means you don't listen. So you said that the raster is made up of regular grid squares. So you have squares. So raster is the right one. Then vector is the left one. Okay. So please listen to what I'm saying. If you listen, you may understand what I'm talking about. So please, I intentionally asked that question. And most of the time when I ask it, people are not listening to what I'm saying. So don't be hard on yourself. You're not the only one. Okay. All right. So I've talked about all these already. Remember that raster is able to store continuous data compared to discrete data. Let me explain it to you. When you take something like a building, the building outline is enough to define it. When you take something like a region, Greater Accra region, it's easy to define rigidly that this is where it ends. Okay, but when you say a forest, really sometimes you don't even know where it starts, where it ends. We may have an idea where it's about to start. Okay, maybe the forest is there, further away, you are inside the forest. Okay, that's continuous data. Let's talk about something like elevation. Okay, it's continuous data because everywhere you go, there's a height value that can be associated. Are you okay? All right. So the advantage is also that the vector data model is very beautiful. It's nice for cartographic. Cartography is map making. Okay. Please, this is a lecture. You are supposed to be making notes and trying to follow what I'm saying. And that's how your questions will come. I'm your examiner. Discrete features such as customer locations, you see, that's discrete. This is where he lives, that's where he lives. There's no ambiguity. All right, so vector does a good representation of discrete data as opposed to continuous data. Okay. All right, topology is not a relevant concept. I think I already talked about that. So yeah, the advantages and disadvantages, you know, they are like, yeah, one is for the other. If we have graphic output is usually as aesthetically pleasing, that's beauty. Aesthetics has got to do with beauty. Is that okay? So then you see that the raster has a problem with that. You can almost turn it around. Most data that exists since Kwame Nkrumah are actually in vector. Put that in your mind. So it means that you have to do a raster to vector conversion, which software can do. Okay, guys. So yes, when when this session ends, this Zoom session ends, click the link again and join me again. Is that okay? But we are going to continue talking about this. Okay, we're going to continue talking about this one.